Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing various aspects of reliability engineering, so that we can predict the likelihood of the desired performance of the spacecraft mission or any of the subsystems. So, a quick recap of the last session. So, in the last session we discussed what is the failure rate or the hazard rate, and we derived a expression for the failure rate. So, failure rate we defined H t is equal to F t by R t, where F t is the probability density function of the failure probability density function, and R t is the reliability function. So, whenever this H t is constant, so this is the constant failure rate, and basically it can be a function of time. So, this curve we describe, this is called the bathtub, this is called the bathtub curve. So, this shows three regions, that is the early period, or it is called the infant mortality period, then this is the useful or the constant failure rate period, which is the useful lifetime, and this is the wear out failure period, where the wear out of the various systems like the propulsion system or the power system which it happens, then there is the higher probability that the system will fail. So, what we did, we for in order to how to represent it mathematically. So, we used here in this part, it is just the exponential this. If I write the probability function here, the probability function is e to the power minus lambda t. So, this is the probability function where this is constant, but in this case, in these two cases R t is, it is basically e to the power minus integration 0 to t h t d t. So, what we have used this especially here the probability that is the density function of, that is F t, that is the density probability density function of failure, that we have seen that we can use the Weibull distribution function, and the Weibull distribution function depending on various the shape parameters, this is called shape parameters, the beta. So, beta is equal to 0.05, then beta is equal to 2, beta is equal to 5, then beta is equal to 1. So, when it is beta is equal to 1, it represents this is the useful life where the failure rate is constant. When it is decreasing, then the beta value is taken which is less than 1, and when beta is more than 1, it is the rising. Also, we have seen that we can use the normal distribution or Gaussian distribution to represent the wear out period. Also, I mentioned that this particularly the infant mortality period can be avoided by the the burn in tests of the components, and when you qualify those components through the burn in testing, then the probability of there is the infant mortality will be reduced. Then we discussed a term, actually we derived the expression for what is the mean time to failure. So, we use this expression, and when this the probability function is that is the failure rate is constant, then we have seen that this mean time to failure, it is 1 by the failure rate. So, when we use this function, so these are the things we studied in the last session. So, now in this session we will be discussing the mean satellite lifetime. So, mean time to failure we are considering or we have seen that the mean time to failure when we consider a constant failure rate, it is an exponential function. So, that way the reliability will be 0 when t tends to infinity. But we will see that in the case of the satellite, it will have a lifetime beyond which the satellite will not work. So, how to modify the probability density function, we will see that. Then we will see that is the satellite system availability. Now, we will discuss how this availability of the satellite services, it depends on the reliability. We will derive the expression for that, especially for two cases. In one case, we will consider there is no backup in the orbit, there is no backup satellite. The other case, we will consider that there is the backup satellite. So, the reliability function, as we have seen, when the failure rate is constant, we can write it R t e to the power minus lambda t, where lambda is constant failure rate. So, the reliability will be 0 when you when t is infinity, means theoretically after infinite time the reliability will be 0. But for the case of a satellite, it is having a maximum lifetime. So, each satellite has a maximum lifetime. Lifetime u, and after that the satellite cannot be operated. What does it mean? That is, after the maximum lifetime u, the reliability will be 0. So, it is shown here, you can see this curve at time u, it is becoming 0 after that. So, which why that is this time u is there for satellite, because the satellite contains limited the fuel in the propulsion system, which have the finite time. It can work up to 5 years, it can 10 years. So, depending on the what is the capacity of the satellite, the fuel life will be the 5 years, it can be 10 years, it can be 15 years. Once this the propulsion system it does not work, so you cannot control the satellite. So, in that case the satellite cannot be operated. So, this is not only for the propulsion system, it can happen with the power system. So, when the solar power system is got degraded, so it also cannot operates for infinite period. It can operate for a certain period. After that, the efficiency of the solar panels will be so low, that is you do not get the requisite power to operate the satellites. So, it can be power system of the satellite, then attitude and orbit control system, where movable parts like momentum wheels are used. So, momentum wheel again it is driven by the motors. So, if they or control circuit, when there is some problem or there can be failure in the momentum wheels also will have the maximum lifetimes. So, this will decide what is the maximum lifetime of the satellite u. So, after u, you will have the reliability of the satellite as 0. So, now the modified the failure rate you can see in this figure. So, here it is also after u it will become 0, but as the property of the probability density function, if you integrate over the total time space, that is 0 to infinity, then f t dt it has to be equal to 1. So, now we will try to find or the modified this probability density function by which this that is the probability, the properties of the that is the or the basic axioms of the probability theory, that is the total probability should be equal to 1, that is satisfied. We will just see how we can do that. So, this is the probability density function. So, it is given f t is given by lambda e to the power minus lambda t. So, we will write this is f t when it is going to infinity and becoming 0, but for this type where it is truncated at u, we will write f u t as so we will express it in terms of a the piecewise function. So, first we will define from 0 to u. So, 0 to u it is given by lambda e to the power minus lambda t. So, this is between 0 less than or equal to t less than u. Then we do not know what is this what is its amplitude at u. So, we will define a constant that is c of lambda, then e to the power minus lambda t, then we will multiply it by with a function called the Dirac delta function, that is t minus u. So, this we will define at t greater than or equal to u, and this is 0 as it is a probability density function, it cannot have a negative value. So, it is t less than 0. Okay. Now, we will just see what is this Dirac delta function. So, if I integrate 0 to infinity and I take a function g t multiplied by this Dirac delta function t minus u, and if I do this integration we will use g u, means this integration is becoming only I am doing at is this integration will be only at a point. So, that is why it is coming g into u, this value is equal to at t is equal to u, this value is 1. So, I am getting at, and all other points this value of Dirac delta function is 0. So, I can write it like that. So, now as per the probability axioms, it should be 0 to infinity f of u t dt should be equal to 1. So, now if I write this expression this piecewise function. So, I will write it 0 to u, then lambda e to the minus lambda dt, then c lambda integration 0 to. So, this is t greater than u. So, I wrote it greater than 0. So, it is t greater than or equal to u. So, I should write u to infinity. So, this is u to infinity, then e to the power minus lambda t delta t minus u dt. Okay. So, this will give me. So, this should be equal to 1. So, this implies minus. So, this if I integrate it, I will get minus e to the power minus lambda t integration 0 to u, and this is c lambda, and this function only at u, as we have written the g u. So, here my function g t is this function, e to the power minus lambda t. So, I should get e to the power minus lambda u, this is equal to 1. So, this I can write minus e to the power minus lambda u minus plus 1, then c lambda e to the power minus lambda u is equal to 1. So, this 1 and this 1 will go. So, I can write c lambda into u lambda u is equal to e to the power minus lambda u. So, which gives me c of lambda is equal to 1. So, now I can write this probability density function if u t is given by lambda e to the minus lambda t. So, it is 0 less than or equal to t, which is less than u, then e to the power minus lambda u delta t, t minus u, t greater than or equal to u, and it is 0 when t is less than 0. So, now I can write the mean time of satellite failure. Mean time of satellite failure with maximum life u. So, tau will be equal to. So, again we will use the expectation. So, it is 0 to infinity, then net number variable t multiplied by the probability density function f u t dt, and this we will get 0 to u t lambda e to the minus lambda t dt plus u lambda u to infinity t e to the power minus lambda u delta t u dt. So, now what I will do, I will write it the previously we wrote 0 to infinity t this function, that is the probability density function is the mean time to failure. To in terms of mean time to failure if I write, so I write it 0 to infinity t and then the probability density function lambda e to the power minus lambda t dt. Then what I need to do, I am doing it 0 to u. So, I need to subtract it from it u to infinity. So, it is t then lambda e to the power minus lambda t dt, and this is the same as we have written u infinity t e to the power minus lambda u delta t u dt. Okay. So, now what is this? This is nothing but the mean time to failure capital T, and this I can write as the way we have written previously by integration by parts. So, the first part is T and the integration of the second part, that is minus e to the power minus lambda t, and we will put the limit u to infinity, this is the limit. Then the derivative of the first function is derivative of the function is 1. So, it is lambda u to infinity, and then the integration of this is minus e minus lambda t dt, and this is nothing but, since it is a delta function is there. So, we have to compute we have to write only this expression at t is equal to u. So, if I do that, then it is u e to the power minus lambda u. Now, this is t and this I can write u, so instead of u it will be t u, then e to the power minus lambda u. So, this is the infinity. Okay. So, the first part will be 0, the way we argued in the last session, that is when at t is equal to infinity, this term is 0, okay, and at t and but t is infinity, but before become the t infinity, this becomes very sharply, it becomes very small value. So, that is why I can write at t is equal to infinity, this whole term is equal to 0, and then I can write that is a minus term will there. So, minus minus and another minus. So, it is minus u t u lambda u. So, this is the term I can write, and this I can write as minus u lambda u by lambda. Then I have this term, that is u minus lambda u. Now, these two term will cancel it out, and this I can write as, now t is equal to 1 by lambda. So, I can write t minus this t into e to the power minus lambda u. So, a constant for the failure rate, the mean time to failure t is equal to 1 by lambda. So, I can write like this, and finally, I get the expression for the mean time of the satellite failure tau is equal to t 1 minus e to the minus lambda u. So, now you see how we have got the expression of the mean time satellite failure with a maximum life of u in terms of the mean time to failure and the maximum satellite lifetime, and it is the failure rate. Now, this tau by t, it is called the probability of, failure during the maximum satellite lifetime. U. Now, we will take a small example. So, let us consider the MTTF, that is minimum time to failure of a satellite t is equal to 10 years. And its maximum lifetime, that is u is maximum lifetime is equal to 5 years. 5 years, then calculate the mean lifetime of the as well as the probability of failure before u. Okay. So, you see already we know that is the mean time of satellite failure tau is given by the mean time to failure into 1 minus the maximum lifetime by t. So, here t is equal to 10, then it is minus 5 by 10. So, it will be 10 multiplied by 1 minus 0.61, and this gives you 3.9 years. Okay. And you can calculate the probability that it will fail before the maximum lifetime of the satellite. So, it will be tau by t. So, this is basically 0.39. So, 3.9 divided by 10. So, so you can see, so these are the things, just a table I have given, you can calculate and verify this table. So, it gives the maximum lifetime and the mean time, that is the mean time to failure. So, mean time to failure has been taken 10 years, and then if you consider the maximum satellite lifetime is 1/3, half or equal, and then what is the probability that they fail. So, whenever so you have seen in from this table. So, whenever t is, that is the u is increasing. So, in that case this is the probability is the failure is increasing. Okay. Now, we will start that is, it is called the system availability. So, now the system availability, it is it depends on the what is the in what way I can we have designed it, or what is the available satellites, what is the launch failure, all those figures comes when I consider a satellite system availability. And then I think we will consider it in our next session. So, we will discuss what is the satellite system availability, and we will consider two cases. In one case, we will consider there are no backup satellites available, and the other case we will consider where the each satellite is having a backup. Okay, thank you very much.